So as Kevin mentioned, we've got a strange looking title for this talk. So without any further ado, we'll start with the cheese. So apparently these days you can go online and you can buy food. So for example, you can put in an order for a kilogram of cheese. In the morning and the afternoon it will arrive on your doorstep. 250 years ago you wouldn't be able to do this. And I know what you're thinking, there was no internet 250 years ago. Well, that's probably true, but more importantly, there was no kilogram 250 years ago. So we tend to take the SI units for granted these days, and we forget that they're actually a fairly recently invented man-made thing. And we think that everybody understands what the SI units are. So this talk is going to be divided into two parts, as Kevin's mentioned. I'm going to talk about the history of the SI and the motivation for adopting it worldwide. And then Farzan is going to talk about what changes are going to be happening on the 20th of May this year, which is World Metrology Day, which is the Monday after next, so it's not very far away, and what impact those changes will have on science and society. So during this talk there'll be a bit of a timeline along the bottom there just to show where we are in the history. So this is today, 2019. So if we go back more than 250 years ago, there's no particular date on there, but if you looked around the old towns in Europe, you would often find standards of measurement. So each town had their own standards for measurements of length, mass and volume, and they were often embedded in some structure in the town square. So for example, there might have been an iron bar which was representing a length standard cemented into the foundations of the town hall, for example, or perhaps there'd be a statue with sort of two marks on the statue indicating a length. So for example, if you go to Dubrovnik in Croatia, you'll find this thing here, this statue which is called Orlando's Column. And so Orlando was a knight. This thing dates back to the early 1400s. Orlando was a knight, and legend has it that he saved the town of Dubrovnik from a 9th century siege that sort of went on for sort of 15 months. And so the citizens of the town were very grateful, so they erected the statue in his honour. Unfortunately, that legend's probably not true, and in fact, the statue represents a town that was under the protection of the Hungarian-Croatian king. So it's really it's a sign of liberty. So in this town, the standard of length was the length of the forearm on the statue. So traders used to compare their lengths of fabric to that length. So because, as I said before, Orlando was a signal of a sign of liberty, you'll find statues of Orlando. He's also called Roland in other towns in Europe. And so if you go to Bremen in Germany, here's another statue of Roland or Orlando. And the standard unit of length in Germany was the distance between those 2 points on his knees. And so in modern measurements, what was called the Dubrovnik L, ELL, which is the unit of length, was 51.2 centimetres. And in Germany, the Bremen L was 55.9 centimetres. So it's the same Roland, same statue, but different units. If you go to Trafalgar Square in London, you'll see a plaque on the north wall, and it has some of the imperial units, the foot, 2 feet, and the 3 feet, or the yard. And also, if you look along on the ground in Trafalgar Square, there are plaques that have larger distances, such as 66 feet, which was called a chain, and 100 feet. This thing was installed, I'm not going to put the date on the screen, but this thing was installed in 1876, so I just want you to remember that date because we'll come back to it. So it was really useful for trading within a town to have your own local standards, but it meant that it was difficult to trade between towns, because each town essentially spoke a different measurement language. And at one point in Europe, there was something like 27,000 different standards for volume. So it was really difficult. Also, having the local measurement units that everyone used within a town was good for the local authorities to collect tax. If you can measure it, you can tax it, and so it was very useful for them. So the French Revolution was a time of great change. This is sort of the early 1800s or a bit before that in France. So France was uniting itself into a republic, and so it became really important that the different territories in France could talk to each other. And so it was decided in 1791 to commission the French Academy of Sciences to come up with a unified rational system of measurements based on a decimal system. And the philosophy of the committee can be summed up by a quote by the permanent secretary, who was the Marquis de Condorcet, and it's been commemorated on a French postage stamp. And his quote is, tous les temps, tous les peuples, which means for all time, for all people. So ideally, the system should be available to everybody, and it should persist over time and not change. And so it was decided at that time that they would define the metre to be 1/10,000,000th of the distance between the equator and the North Pole. So the distance from the equator to the North Pole should be 10,000 kilometres. And so they set about to measure that. And so the line had to pass through Paris, through the quadrant that passes through Paris. And it took maybe 8 or 9 years to do this measurement. And they didn't really measure the whole thing. They measured sort of from northern Spain up to north of Paris, but they managed to then extrapolate the rest. And they must have done a pretty good job, because we know today that the circumference of the Earth is pretty close to 40,000 kilometres, so they got the metre right. So once they defined that metre, then they defined a litre, which is 1/10 by 1/10 by 1/10 of a metre, so it's a litre. And if you fill that volume up with water at 4 degrees Celsius, that defined a kilogram. And so based on these measurements in 1799, they manufactured a platinum artefact mass and a platinum artefact metre bar, and they deposited those into the French archives. Unfortunately, the system didn't last particularly long. It wasn't very popular. People thought it was pretty pretentious using this new system. And in fact, in 1812, Napoleon reintroduced some of the old units. He called them the mesures usuelles, or the customary measures, based on the old systems, but defined in terms of the metric system. So the early 1900s saw the Industrial Revolution, so there was huge amounts of industrialization and new technologies, new developments occurring. People were developing railways, and there was steam navigation, and there was sort of massive advances. People were manufacturing huge bits of machinery, and they had to source different parts from different suppliers. So of course, you always want one man's nuts to fit another man's bolts. There are all sorts of scientific things going on, scientific discoveries happening, and better accuracy was required. And so it was finally realised that they needed some universal system of measures that everybody could use. So in 1875, on the 20th of May, which is World Metrology Day, representatives from 17 countries around the world gathered together in Paris and signed what is called the Metre Convention. It's also known as the Metric Treaty. Essentially, that was an agreement to use the metric system. So originally I said there were 17 countries that signed up. Interestingly, the US was one of the first countries to sign up, even though we think the US still uses imperial units. In fact, in government and industry and science organisations in the US, they do use the metric system. It's only out in industry that they use the imperial units. If you think back to the Trafalgar Square thing, remember I said those plaques were installed in 1876. It was a year after the metric treaty was signed. So obviously the UK didn't sign it. At least not originally. They wanted to stick to their own units. But they did relent. A few years later, in 1884, the UK signed the metric treaty. Australia signed it in 1947. Can anyone guess when New Zealand signed it? We are a member. No guesses?
1948.
You're miles out. It was 1991. It was only fairly recently that New Zealand signed up. So these days there are 60 full members of the metric treaty and 43 what they call associate members. So as well as is agreeing for everyone to use the metric system. The metric treaty also created an organisation called the BIPM, which is the International Bureau of Weights and Measures in Paris. There's a photograph of the site. And the BIPM is responsible for coordinating worldwide metrology and sort of overseeing developments of the metric system. Interesting, so the site is just south of the Seine River near Versailles, sort of on the outskirts of Paris, but the site it's on is actually not technically part of France. It's independent territory. So this is an intergovernmental organisation, and it sort of has its own sets of rules. But you don't need your passport to enter the gates. So shortly after the metric treaty was signed in 1875, they decided to make some new artefact masses and length standards. Instead of being based on platinum, these are based on platinum iridium, so there's an alloy. And the iridium makes the metal a lot more stable and less porous. So they made 30 of the length bars and 40 of the standard masses, and they picked one of each at random to become the international prototype kilogram and the international prototype metre. And those were deposited into a vault in the basement of the BIPM. In fact, they're still there today. So the remaining standards that they made, so the 30 and the other 40, were distributed amongst the member states of the metric treaty. And so originally, the metric treaty only covered the units of mass and length, and things like the second, for example, were looked after by the astronomers, because the second was defined originally as how long it takes the Earth to move around the sun, so that was in the domain of the astronomers. But in 1889, so those were deposited in the archives. In 1921, they decided to expand the scope of the metric treaty to include all units, not just length and mass. And so over the next 50 years or so, the definitions of the units evolved, and there were debates as to which unit should be included in the metre convention and which one shouldn't. And this carried on till 1960, where the name SI, which stands for the International System of Units, was officially adopted. And originally the SI just included these 6 physical base units. So we have the candela, the kilogram, the metre, the second, the ampere, and the Kelvin. And a few years later, in 1971, they added the mole. And so most people will be familiar with at least the first 3 of these units. The kilogram is the unit for mass. The metre is the unit for distance or length. The second is the unit for time. The ampere is a unit of electric current, so that would be familiar with people that work in electronics or electricity. The Kelvin is the unit for temperature. People will be more familiar with the degree C unit, but there's a simple relationship between Kelvin and degree C. So a temperature in Kelvin is just a degree C temperature plus 273.15, so it's just a slight shift. So water, which freezes at 0 degrees C on the Celsius scale, freezes at 273.15 on the Kelvin scale. The mole is the unit for amount of substance, so this is used by chemists when they're analysing chemical reactions, etc. And the candela is the unit for luminous intensity. So that tells us how bright light sources appear to the human eye. So it's a very human-centric unit, that one. There's nothing particularly special about which units were chosen here, and even the number of them, 7 of them, which are called base units. All of the other units can be derived from these base units. So for example, the unit of force, which is the Newton, is a combination of these. So a Newton is a kilogram times a metre divided by seconds squared. So all of the other physical units can be related to these. But so there's nothing special about them. They just happen to be useful to serve our everyday industrial and needs and scientific needs, etc. And there's also nothing particularly special about the size of the units. They are designed to be suitable for human purpose. So for example, 1 metre is about the length of a human arm. A kilogram is about as much as you can eat in one sitting. And a second is probably about as long as you can stay awake in a talk like this. So it's a nice coherent unit. It's served our purposes. Basically, the three things we want out of it is stability, availability to everybody, and accuracy. But over the years, since 1960, when the SI was formally adopted, some of the units have evolved. So the SI system is not static. It's changing all the time. And a good example of that is the meter. So as we said earlier, the meter used to be defined in terms of a length of metal bar, and it's in a volt in Paris. That was based on the measurement of the circumference of the Earth. But the problem with having an artifact standard like that is it becomes infinitely valuable. And if, for example, it drifts in length, or if somebody damages it, then by definition it is still a meter, so everything else in the universe must change size. So, and it's also having an artifact standard that everyone has to go back and compare with limits technological advances. And so this was recognised quite early on with the meter. And so in 1960, they redefined the definition of the meter to be a certain number of wavelengths of light that's emitted by the krypton atom. And defining it that way improved the accuracy of length measurements by about a factor of 25. But even that wasn't enough, and so soon after they redefined it again. And so we know from Einstein's theory of relativity that the speed of light is a constant, no matter how you observe it or where you observe it. And so it's a really good foundation for a definition of a unit because it's unchanging in the universe. And so in 1983, the definition of the meter was defined by setting the speed of light to be this exact number here. So previously, people used to be able to measure the speed of light. Now this is it exactly, and it's never going to change. And so the meter now is defined as the distance that light travels in a very short, small fraction of a second, where that fraction of a second is 1 divided by this number. And so having the meter defined that way actually improved the accuracy by another factor of about 40. But it means now that anyone can use any method they like to determine what a meter is, as long as they can have the apparatus and can relate their measurements back to the speed of light. And essentially we've now taken the meter out of the volt, both literally and figuratively. So, and the meter now defines, well, the speed of light defines not just the meter, but also the kilometre or the nanometre. Any scale that you want to measure, you can measure by relating your measurements back to the speed of light. So this process of defining the units in terms of a fundamental constant is going to be a constant feature of the rest of the redefinition that's coming up. And so Farzana is going to talk about how all the other units have changed to basically follow the pattern of the meter.
Thank you.
Is your thing switched on?
Yeah, it's on. So since 1983, the definitions of SI-based units have not changed. But in November last year, all the member states of the Meter Convention gathered in Versailles to vote on a new set of definitions for SI-based units. Our director, Fleur Francois, traveled there to vote on New Zealand's behalf. That's how it played out. Yeah. In case you didn't hear her, she said yes. And so did the rest of the world in a unanimous vote. So what does this really mean, and how is the impact of SI redefinition on our lives? As Peter mentioned, meter has been already defined based on a physical constant, and the same goes to two other SI-based units. But because of keeping the consistency for the definition, some wording is changed for 3 of the units that has already been defined. But for 4 of them, it's not just confined to the wording, the whole definition is going to be changed. And by the way, these changes are officially being implemented on the 20th May this year. So the second unit that we discuss is the second. The second is now defined based on a physical constant, which is the transition frequency of a cesium atom. It might not sound as intuitive as, for example, an older definition of the second, which was one specific fraction of a day. But clocks that work with this technology are called atomic clocks and have the accuracy of 1 second per 30 billion years. And this high accuracy gives us the ability to use technologies like GPS and the internet these days, which our lives really rely on. And New Zealand, MSL in New Zealand keeps the time for New Zealand with 3 atomic clocks. So the other unit that is not changing is the candela. Candela describes how a source of light appears to the human eye. And one candela was defined to be as bright as a standard candle at the time of the definition. The constant unit that is used to define the candela is KCD, which is a conversion factor for the original or absolute power divided by the power of that source that is perceived by the eye. So that is a constant conversion factor and is shown with that number. Also, MSL keeps candela for New Zealand so that the operating theaters are bright enough for a surgeon to see the patient. On to the units that are actually changing. Kelvin is one of them. So, so far, or at the moment, we use the triple point of water to define the temperature. That is defining the temperature based on 3 states of water, which is solid ice, water vapor, and liquid water. If all these states of water coexist in an equilibrium, the temperature at that point would be 0.01 degrees C, or 273.16 Kelvin. This is a very reliable method and reproducible, so that's why we have been using it for a long time. But the fact that it only relies on 1 point of temperature to define the whole spectrum, it's not very accurate, especially for extreme high and low temperatures. So we need to use another method to be able to get more accurate readings for temperature. What we use is the Boltzmann Constant, which is shown with that number at the bottom. In 1800, Boltzmann was a scientist who was monitoring temperature and really found out that temperature is nothing but monitoring the energy. So there is a relation between energy and temperature. Later, Planck, another scientist, gave a ratio to the energy and temperature and defined that ratio after Boltzmann and called it Boltzmann Constant. So now in this slide, I'm gonna describe a very interesting fact that shows us how we are ready now to use Boltzmann Constant to define our temperature. If you see from 1900, we have the accuracy of the measurement for the Boltzmann constant. And this scale is logarithmic, so it shows a very accurate measurement at the moment because the accuracy is going, uncertainty of the measurement is going from a bit over 1 to less than 0.001. So the first 2 measurements of Boltzmann constant were done by Planck and Einstein. And one of those last ones there is done by one of our colleagues at MSL. Meanwhile, temperature has, the accuracy or the uncertainty measurement of temperature has not changed a lot. And we see that at the moment, we can measure Boltzmann constant much better than we can do temperature. So now it's the right moment to try to define temperature based on the Boltzmann constant, because if we use the Boltzmann constant now, we don't upset any temperature measurements which have been done at the past. So this is the definition of the temperature that we are using currently, which is 273.16 Kelvin, which is the triple point of water cell temperature. And the Boltzmann constant has some uncertainty in its value, while the temperature doesn't. But on 20th May, we will no longer be sure about the temperature of the triple point of water cell. That's why we have to keep a close eye on it. But at that time, we know the Boltzmann constant accurately and exactly enough to be able to measure temperatures based on that. Next unit that is changing is the kilogram. Right now, 1 kilogram is the mass of the international prototype kilogram, which is kept in a vault in Paris. Now, it's very unlikely that someone is going to run off with a kilogram because it's kept in the vault in Paris. But measurements historically and currently show that this international prototype kilogram is drifting in mass, and scientists really don't know why that's happening. So given that our kilogram measurements relies on an artifact, it's better to find another physical constant which enables us to measure the kilogram independently. So this is the definition of kilogram right now, which is the IPK, and we know exactly its mass. And that's Planck's constant, which is the physical constant we are going to use to define the kilogram after 20th May. Planck's constant is a very familiar constant for physicists, and it comes a lot in quantum physics, especially with the advancement of quantum physics in the last 100 years. I just want you to look at the units that Planck's constant has. It's kilogram meter squared divided by the second. So if we know exactly how much the Planck's constant is, and if we know the meter and the second based on physical constants, then we are able to exactly make sure how much the kilogram is. So on 20th May, we will no longer know what is the mass of the IPK, but we will surely know how much the Planck's constant is. And that will help us to be able to judge the kilogram much accurately. But New Zealand still will keep the standards for mass for New Zealand, so that for example, trades are easy because we want to make sure that other countries rely on our measurement, that, for example, 1 kilogram of dried milk powder is still 1 kilogram of dried milk powder all over the world. Next unit up is the ampere. Befitting the name, the logical constant to define the ampere is the electron charge. And electrical community has been ready to do this redefinition for a long while now, but they have not been able to do so. And that has a reason. The reason is that the electron charge, the reason relies in the electron charge definition, because it is indirectly related to force through mass. So if we don't know mass based on a physical constant, then we will not be able to measure the ampere accurately. This slide shows the old definition for ampere, which 1 ampere is the current in 2 parallel wires, which are infinitely long and stay 1 meter apart, while a force of 2 × 10⁻⁷ Newton per meter is applied between them. And that's the electron charge constant, which we are not sure. That's why we have the question marks there. But after 20th May, we will make the electron charge constant to the most accurate result that we've got so far. And then we will not be sure what is the current in that wire. Although it's very close to 1 ampere still, but it won't be 1 absolute ampere anymore. The next unit that we talk about is the mole, but not this mole. We want to talk about the chemistry type of mole. So at the moment, 1 mole is the mass of a substance with the entities that are equal to atoms in 12 grams of carbon-12. But after 20th May, we will use the Avogadro's number, which is a familiar constant for us. So we will use this number as the number of moles. We will use this constant as 1 mole. And we will fix Avogadro's number as we fix Boltzmann constant, Planck's constant, and electron charge. So to summarize, we are moving forward from a set of units that were laid back by old technology and physical objects to a system of units that are defined based on the physical properties of nature. And what does really this redefinition give us? So the first thing that it gives to us is the accuracy. So our measurements would be accurate everywhere in the world as long as we are using these physical constants. And these physical constants really will stay constant as long as the laws of physics that we know currently stay the same. So with accuracy comes availability and comes a stability, because we will be able to use these accurate measurements everywhere at any time. If we want, we can use them in a space, on the Mars, or even on any other planet that you'd like. So you will have them available and accessible everywhere. But the main point is that a measurement standards laboratory will still keep the units for you, and you don't have to be worried about it, because everyday life is not going to be changing, although for us metrologists it's a very important point in our career, but still water will freeze under 0, and still 1 kilogram of cheese will be 1 kilogram of cheese. So unfortunately, if after 20th May you start to get speeding tickets, this doesn't mean that it's related to redefinition or it's because the calibration is not done right. This means that next time we should slow down. So with all that being said, sometimes we are asked, why do we need to know, for example, 1 ampere to the accuracy of 1 nanoampere, or even more? I want to ask another question. When we hear that people want to improve the polish on their lens in a telescope, we don't question why, because we know that they want to get an image with a better resolution, something like this. To the same extent, redefining a psi-based unit based on physical constants will lay a foundation for technological advancement in the future. Who knows what these new definitions would have for us in the future? And who knows, one day you might want to buy your cheese in nanograms. Thank you.